welcome to your next microbiology lecture. Controlling growth of microorganisms. So it's really important to think about how we need to control growth of microorganisms because we don't want infection, if nothing else. So we're looking at to eliminate or reduce microorganisms in a wound, but also in our food and in our environment. So let's look at some of the different ways we can think about that. So this topic is really going to be an exercise in vocabulary, lots of new words, but again, most of them make sense. It's the subtleties between them that you'll just have to work on and keep using until you have them down and can use them comfortably. So antimicrobial, chemicals or other agents that kill microbes or inhibit their growth. Again, we need to go back and define a microbe, something tiny. So a microbe is going to be a pretty general term. It's going to include all of our prokaryotes, both our bacteria and our archaea, but then we also have to include our viruses, as well as all the single-celled and tiny eukaryotic organisms that are of interest to us in microbiology because oftentimes they are infectious. So antimicrobials, broad. Biocides, even broader. They're going to damage all forms of life. Antibiotics, they're going to be specific to microbes. Germicides, agents that kill microorganisms and inactivates viruses. When you're considering controlling microbial growth, you have to consider what your goal is. And this is kind of the spectrum that we see from the most stringent being sterilization. So if you have an object that is sterile, you've sterilized it, and sterilization is removal or destruction of all microorganisms and viruses on or in a product. That's a lot. That's it. You're done, right? Nothing will come back from that. And our big sticking point that we're going to see throughout this topic is endospores. It's one of our highlights. It's like, this does everything great except for endospores. But if we're sterile, we've gotten rid of endospores as well. It doesn't include prions. They're their own special category, and we'll talk about them later. Disinfection, elimination of most or all pathogens in a material. So it implies the use of biocides, but most or all, if you're lucky, there may be some viable ones. So it's not as stringent as sterilization. So disinfectants then are going to be the chemicals generally that we use to disinfect inanimate objects. Germicides, so bactericides, fungicides, and virucides. Antiseptics, so these are going to be antimicrobial chemicals that are non-toxic enough that we can use topically on our skin or other body surface. Decontamination means that we're going to reduce the number of pathogens on or in a product to a safe level. So here it's like we know we're not getting rid of everything, but we're reducing it a significant portion to something that we have deemed safe. And if we're looking at that with regard to infection, that means below a critical number for infection. Sanitation or sanitization is going to be our least stringent. It implies a process that substantially reduces the microbial population to meet accepted health standards to minimize the spread of disease. Right? So again, this is pretty arbitrary in the sense that we're substantially reducing the microbial population. The health standard then is determined by something, and it's going to be different for different surfaces, for different diseases that could potentially be there. But, you know, again, by reducing the numbers of microbes there, we are certainly reducing the likelihood that they can infect and harm us. We can also consider preservation of materials, particularly food products, right? So preservation, the process of delaying spoilage of perishable products. So we're going to generally think about storage conditions or chemical preservatives that will slow microbial growth. So if something is bacteriostatic, it means that it's a chemical preservative that inhibits the growth of bacteria, but it's not going to kill them. Pasteurization, brief heat treatment that reduces the number of spoilage organisms and destroys pathogens without changing the characteristics of the treated product. And that's going to be a key attraction to this is if I want something specifically, if it's a food product, to be unchanged except for the fact that it no longer carries pathogens. That's what we call pasteurization. Cold pasteurization is going to achieve the same end. So anything that achieves the same end without using heat, we call cold pasteurization. Just some bonus vocab, and that is HAIs, healthcare associated infections. Whenever you're in a healthcare environment, let's use in a hospital, for example, you have more people concentrated that are vulnerable because they're sick, because their immune systems are already stressed or aren't functioning. And you have a higher concentration of individuals with pathogens because people are there because they're sick and they bring their pathogens with them. So it's something to kind of think about because we need to be particularly careful about how we maintain our environment and control microbes in a healthcare setting. So good aseptic technique is the start. Just for fun, thinking about biosafety levels, we think about labs and where we work with microbes. So if you're working in a diagnostic lab, so when you send a sample from a patient out to being analyzed, it's going to go to a lab. When you are working with labs, or you're working with organisms in a molecular biology lab, or you're researching microorganisms, your facilities are going to fall into one of these four categories. One being the least stringent, four being the most. We in this class will work with BSL-2 level organisms, and using the PPE that we have, in addition to the room, we have a biosafety level 2 facility, but it gets much more stringent as you hit 3 and 4. Don't worry, again, I'm not going to ask you to memorize any of this stuff, but it's just good information, just so you're familiar and you've been exposed to it. Now, when we're thinking about using antimicrobials or controlling their growth, we've got to think about some things here. So, what is the composition of the target microorganism population? Have they established themselves? Is it a biofilm? What is the species? So we're going to point out some noteworthy opponents next. Or is it a mixture of species? Again, if it's a biofilm, it probably is. And that's going to impact our success. And choosing the correct procedure is going to be significantly impactful. So resistances that might be present, and then substrate. So, I mean, you can use your Bunsen burner and incinerate things, but not everything can handle a full out flame, and you want to preserve your couch or whatever it may be that you may be looking to control microbes on. So just some considerations. So noteworthy opponents. This is a list that's probably worth committing to memory or being at least very familiar with. Whether you're going on to healthcare or not, these are the things to look out for. You follow standard protocol, these are the things that are going to sidestep those protocols. So let's go through the list. Bacterial endospores. So we talked about endospore formation. Bacillus, Clostridium, other genera are going to be capable of forming endospores because not every prokaryote is, but those that are, we need to be familiar with them. Extreme heat or chemical treatment. So they are resistant for a reason. These are things that are made by the bacterium to be like, hey, things are getting bad. We want our species to move on, so I'm going to hunker down in this state and survive it. So they're tough. So you just have to be aware and make sure you hit them hard so that they don't germinate and start a new population. Protozoan cysts and oocysts. So these are stages in the life cycle of certain intestinal protozoan, the ones that we're most interested in because they infect us. Giardia, Cryptosporidium. Again, they seem to be resistant to disinfectants, but again, boiling works well. And we'll talk about physical and chemical means, and so these are some highlights beforehand. Mycobacterium species. So it's a diaderm, meaning it's a gram-negative, but it has this really hydrophobic cell wall. And I'm trying to read and learn more about that. But this mycolic acid it's a waxy material in the cell wall, and it makes them very resistant to chemical means. So this is also now an acid-fast species, which we talked about and we'll talk about more. But tuberculosis happens to be a mycobacterium, and of course, that is a disease that we are wanting to avoid. Pseudomonas species, again, very common environmental prokaryotes. They are opportunistic. We often have Pseudomonas species on our skin, but they tend to be resistant to disinfectants. And non-enveloped viruses. So we haven't talked about viruses yet, but we will. Viruses with an envelope, that means they've taken a piece of the cell membrane of the cell that they infected and taken it with them. When that membrane is important to their ability to enter a new host cell, because that's where all the protein receptors are. But as we all know, a lipid membrane is vulnerable to desiccation, and it's not physically very robust. So enveloped viruses tend to be easier to control, but non-enveloped viruses are just going to be the protein capsid encircling a piece of nucleic acid. So they tend to be very much more resistant. When we think about controlling microbial species, numbers matter, right? So it's simple math. The larger the population, the more time it takes to kill everything, to be sure. So kill rate is a fraction of the population killed over a given period of time. And so if there's anything that you can do preemptively to prepare your substrate or your product or your person or whatever it is that you're trying to control the bacterial population or eliminate it, reducing the numbers helps. So washing reduces the numbers. Washing eliminates biofilms. Washing eliminates dirt and grease and body fluids that all can inhibit the efficacy of certain chemical disinfectants, and we'll talk about that a bit later. So that physical removal of as many as you can, why not start there? It's going to make then your specific approach much more effective. So we're going to quantify this ability to kill things with what's called the D value. So the D value is called the decimal reduction time, the D value. It's the time in minutes it takes for an antimicrobial treatment to kill 90% of a microbial population under specific conditions, right? So if it's 10, now you've taken them down to 1, right? So you move the decimal over 1. So we can use this for chemical treatments, but usually think about it in terms of heat. How long do I have to keep this thing hot? How long do I have to boil it? How long do I have to keep it at elevated temperature? But it can be used in reference to chemical treatments. As you'll see, certain surgical equipments, if you're going to go after a chemical disinfectant or sterilization, it may be hours with a submersion in a particular chemical treatment. So we can graph that like this. There's your D value. Again, at time 0, you've got a population of 10,000. And then every 5 minutes, you're going to reduce that 1 order of magnitude, 1,000, 110, down to 1. Again, here's a slide that makes a whole lot of sense. Not something I'm going to hold you accountable for, but something that certainly is worth thinking about. Critical, semi-critical, or non-critical instruments when it comes to, again, healthcare, interacting with our bodies. So those that come in contact with body tissues, anything that's going to go inside you, needles or pierce you or cut you, it has to be sterile because you're sterile inside. And things that want to eat you, the tissue inside, fantastic, right? So we want to avoid that. Semi-critical instruments, so now we're going to come in contact with mucous membranes, but we're not going to actually penetrate the envelope of the body. So endoscopes, etc. Apparently, endospores can be permitted because our mucous membranes are particularly effective against them. So that's good to know. Semi-critical. Non-critical instruments, unbroken skin, right? Stethoscope, blood pressure cuffs, stuff that we're touching, non-critical. So we're going to oftentimes think of this on a level of sanitation. And so let's talk about how we do that. Physical and chemical methods. We're going to go over each in turn. We'll start with physical, run through the list, then we'll hit the chemical, run through that list. Again, familiarity with these is the most important thing. Having like a detailed knowledge of each of them is not necessary at this time. Physical methods. Here's your list. And it looks a little onerous. But again, these things aren't particularly alien, nor are they complex. Moist heat, dry heat, filtration, irradiation, pressure, right? That's your main list. Then, can you talk with a little bit more detail about moist heat per se? How do we apply it? What are the mechanisms? Dry heat, what have you. So let's go through each of these in turn. When it comes to moist heat, boiling is your easiest approach. Generally, 5 minutes of boiling will clean most everything out, but not endospores. Pasteurization, it's kind of like the opposite of those 5 minutes. It's hot flash. So high temperature, short time is what we think about. So the milk that we drink is 72 degrees Celsius for 15 seconds. Ultra high temperature methods, 140 degrees Celsius for a few seconds, and then rapid cooling. So that is going to have to be under some pressure because we've gone over boiling. Pressurized steam, the autoclave is like your standard instrument in any lab setting or a medical setting that needs sterile equipment. Things need to be able to survive increased pressure and increased temperature, but glass and steel do just fine, and then many plastics will as well, as long as you know that they're the type of plastic to do that. So steam at 15 psi, which is a whole extra atmosphere, and then 121 degrees Celsius. This will take out endospores, and we usually autoclave things for about 15 minutes. So autoclave tape is something that is standard in near any autoclave. It's a tape that has colored stripes on it that you can't see until it experiences 121 degrees for about 15 minutes, and then it'll become striped black. So it'll go from white to striped, and then you know that the tape in the autoclave experienced the proper conditions. Because a piece of sterile glassware goes in clean, it comes out looking the same. So unless you have some control to know that it was sterilized, that's what the autoclave tape is for. And I'll show you guys this in the lab. Again, prions, which we'll talk about later, which are kind of infectious proteins, it's super, super tough. You'd have to like hit them with chemicals even before you autoclave them. So 1 molar sodium hydroxide, and then you autoclave it. That's rough stuff. So this is just a diagram of that autoclave. Again, it's just a pressure cooker, and we'll take a look at the one we have at school one of these days when we're in the lab. Dry heat, this is your Bunsen burner, right? Incineration. So if you chemically destroy your carbon compounds, then you're not alive anymore. So the powdery residue left after burning a substance is the ash. So flaming loop in the lab is an example of this. You can also use a dry oven. So cranking your oven up to 160 to 170 degrees Celsius for 2 or 3 hours generally is how you do it for glassware and lab equipment. Again, from a lab point of view, if I'm working in an environment where I'm going to be isolating RNA or working with RNA, I need to actually make sure my equipment is RNase free, and the autoclave won't do that. So RNases are proteins that eat up RNAs. And if isolating RNAs are your goal, then having RNases on your equipment is no good. So it's an extra step, and to be very deliberate about it, you have to make your equipment RNase free, and the dry oven for 2 to 3 hours will do that. Filtration is next. Again, pretty straightforward. I'm going to take a membrane. I'm going to poke holes in it. Anything that's bigger than the hole gets stuck on the membrane. Right? So the standard for sterilization is a 0.2 micron pore size. And so we have a bunch of these in the lab. We can use them actually in a syringe as well, is the most common way I do it, because I'm usually using small volumes. So viruses can get through generally, but most cells will not. From an air side of things, as opposed to liquid, we look at the HEPA filter as the gold standard. So generally, we see a 0.3 micron cutoff for a good HEPA filter. And they were originally designed to clear the air of radioactive contaminants during the Manhattan Project. So this came out of World War II technology, and it's been great since. You'll find them in air conditioning units. You'll find them in your vacuum cleaner. Irradiation, ionizing radiation, UV radiation, ultraviolet germicidal irradiation, which is something new to me, and then of course microwaves, all on the electromagnetic spectrum. basically, when you're using high energy EM, you are breaking DNA. And if you break DNA enough, things don't work anymore. You can damage membranes. Indirectly, that irradiation is going to produce radical oxygen species, which we talked about earlier. They're going to do their job, damaging proteins and membranes. Endospores tend to be more radiation resistant, so you have to be aware of that. And some bacteria can be more sensitive to it. This would be, in effect, a cold pasteurization technique. You can use UV. The problem with UV is that it is very short range. You need to be very close to your UV lamp for this to work well. Again, it's going to damage DNA and denature proteins. It's most effective against actively multiplying organisms because they're trying to replicate their DNA. And by damaging the DNA while it's trying to replicate is a great way to mess things up. Won't work for endospores. Again, UVGI, this ultraviolet germicidal irradiation for food products, is not something that I've seen a particular label for, but it seems like a fine way to surface sterilize or at least reduce bacterial populations in a non-invasive manner. Microwaves are great. I know people who throw their sponge from their kitchen sink in the microwave for a minute and say, oh, it's sterile. And that's probably not the case, just because microwaves are so inconsistent in their heating of their target, like a solid or even a liquid. So be aware of that. But, you heat something up enough and you're going to start killing things. High pressure. So this is one that we're not going to see except really in an industrial setting. So high pressure processing is a lot of the food and packaged goods that we see. Pascalization, because a pascal is a unit of pressure. So it is also another version of cold pasteurization. The pressures that we're going to experience are going to be effective for controlling microbial populations are incredibly high. So 120,000 psi, where 1 atmosphere is just about 15 psi, is a considerable amount. So that's about 8,000 atmospheres. So one of the companies that makes these industrial sets of equipment for food processing, give this example at 6,000 bar. That would correspond roughly to the weight of 3 jumbo jets acting on the area of a smartphone. So that's going to be a lot of pressure. So those are our physical means. Now let's consider our chemical methods. I took this sentence directly from a book. It's like vocab practice, right? Going back to our earlier slides. So germicidal chemicals, what's a germicide? Are used to disinfect. What's a disinfection? And in some case, sterilize. Ooh, we now know disinfect and sterilize are not the same. Do we know what they mean? Most are biocidal. What's a biocide? And react irreversibly with protein, DNA, cytoplasmic membranes, and or viral envelopes. So this is what we're doing. We're taking nasty chemicals and throwing them at bacteria, and they're going to do a bunch of damage. Their exact mechanism is often poorly understood. So sometimes we don't know exactly how they're working, but we know they work. Some are non-toxic enough to be used as an antiseptic. What's an antiseptic? So go back now and make sure that that's vocab that you're starting to use more and know the differences between those. Here's our list. And this list is even more intimidating than the physical control methods list. But we're not going to get into too much detail with this. We're going to hit the highlights. I'm going to give you some pointers on using each of these. But again, having heard these terms and being familiar with them is enough. I'm not going to be like, explain to me how ethylene oxide works, right? Because that's something you're probably never going to use because it's nasty. But alcohols you're going to use all the time. Phenolic compounds you're probably going to use a bunch. And halogens, of course, because that's like bleach. So let's just go through some highlights. Again, when you're using chemicals, you have to consider the situation. What is the toxicity? The things that hit microorganisms hard are probably going to be bad for you and to some extent the environment as well. So how fast does what I'm using break down? Does it persist in the environment? Does it hurt me? Organic matter. So this specifically is a bleach thing. So bleach interacts with organics. And so if you have a bunch of organics around that are not your target, they're going to mop up your bleach, effectively reducing the amount of bleach that you're adding to take out your microorganism. Phenolics are less so. What's your substrate, right? So can you bleach everything? No, you can't, because some stuff will break down with bleach. So you have to be careful about that. So you have to think about that as well. What's left behind? How long does it last? Cost and availability. Some things work really, really, really well, excuse me, but they're very expensive or they're hard to handle. And then environmental risk. Again, alluding to the first thing in toxicity, it's like, does this thing screw up the environment? Is it safe? Is it going to persist? Is it going to hurt me in the long term? So just a quick list of points of note, and this is good enough. So alcohols. The thing that's key about alcohols is everybody goes American on it. It's like, oh, because America's more is better, right? But that's not the case, and most times that's not the case. So we want to be un-American with our alcohol. It works best at 60-80% in water. Aldehydes, just chemical cross-linkers. So you might think of formaldehyde or glutaraldehyde. These are things you might be familiar with, but it's a nasty. Biguanides, so chlorhexidine is one of the ones that is most common and popular. It disrupts cell membrane integrity. Ethylene oxide is just super nasty, but because it's a gas, it can penetrate small spaces. So like if I wanted to disinfect electronics or a computer or something, the best thing to do would be to use ethylene oxide. Why would I want to do that? Well, if I'm taking something up into the space station where I don't want to bring bacteria with me, nooks and crannies are where things love to be. And so how do you really disinfect stuff? Unless I build my computer in a clean room, like a sterile room, it's not going to work. So I have to treat it. So that's where you would use something like a gas. But we generally, in our everyday lives, don't need anything like that. Chlorine, bleach, halogen, right? Iodine. So iodophores, the key to them is if you ever have one in a bottle, it's an iodine solution. You need to dilute it for it to be effective because it has a carrier molecule that you want to make sure you knock off for it to work. Metals. So we were talking about this earlier in the sense that why are door handles and oftentimes hardware that we touch every day made of metals. One, because they're durable, but also because they resist bacterial growth. And one of the reasons that is that because they're reducers, right? You can, not every metal, but like colloidal silver we've seen, but you're going to mess with thiols on proteins. You're going to mess up proteins with metals. Oxidizers, just remember your radical, your ROSs, right? And phenolics, that's Lysol. So tend to be aromatic rings, like look up phenol, and you can look at that if you want to look at the chemical structure. And then quats are quaternary ammonium compounds, and they're very common sanitizers, right? So if you have that list, you're fine. Now, finally, let's just think about preservation. This idea, if I have something in an acid, it can tend to reduce bacterial growth, except for our acidophiles. Nitrites and nitrates are oftentimes preservatives in foods as well that will preserve them. Low temperature storage, refrigeration, freezing. Again, there's always some bacteria out there that's the exception to that. So we don't want to forget about our psychrotrophs and psychrophiles. And then, of course, reduced available water, right? Salting, sugaring, drying, osmotic stress. Some things are better at handling that, like salmonella, unfortunately. But this is where we get our preserves, our jellies, our beef jerky, dried fruit. All these things are preservatives because when I have a bacteria landing in a very dry or very salty environment, it's much more difficult for it to grow. So that's a lot. Go back, go over these lists again, write them down, talk to each other about them. The only way to really get familiar and comfortable with these is to use them. And so we'll try to do some of that in class as well.